Okay, so let's continue the lecture. And I want to say that maybe in the last lecture here, I wrote this 5 here, and the 5 is in the position of the denominator. Okay, now let's continue. Example 2, a foreign object continued. Investigate the behavior of solutions of equation 5 without solving the differential equation. Solution. First, let us consider what information can be obtained directly from the differential equation itself. Suppose that the velocity v has a certain given value. Then, by evaluating the right-hand side of differential equation 5, we can find the corresponding value of dv over dt. For instance, if v equal to 40, then dv over dt is equal to 1.8. So what's this mean? Let's look at this equation. This is the fifth equation. If v is 40, then dv over dt is equal to 1.8 because 9.8 minus this is 1 over 5 times 40. And it is equal to 9.8 minus this is 8. So this is equal to 1.8. So here dv over dt is equal to 1.8. This means that the slope of a solution v or v of t has the value 1.8 at any point where v is equal to 40. We can display this information graphically in the TV plane by drawing short line segments with slope 1.8 at several points on the line v equal to 40. So let's see figure 1.1.28. Here is the figure 1.1.2 and this is A. Similarly, when v is equal to 50, then dv over dt is equal to minus 0.2. And when v is equal to 60, then dv over dt is equal to minus 2.2. So we draw line segments with slope minus 0.2 at several points on the line v is equal to 50. You can see here. And this is v axis and this is t axis. When v is equal to 50, we can draw the segment, and there are many segments, and each of these segments their slopes are minus 0.2. And line segments with slope minus 2.2 at several points on the line v equal to 60. And look this figure. At v is equal to 60, we draw the segments of which the slopes are minus 2.2. Proceeding in the same way with other values of v, we create what is called a direction field or a slope field. The direction field for differential equation 5 is shown in figure 1.1.3. And let's look at the figure 1.1.3. This is the direction field. Remember that a solution of equation 5, this is equation 5, is a function v or v of t whose graph is a curve in the TV plane. The importance of figure 1.1.3 is that each line segment is a tangent line to one of these solution curves. Maybe can I put this 1.1 point figure here, and yes, I think I can put this figure here. This is figure 1.1.3. The importance of figure 1.1.3 is that each line segment is a tangent line to one of these solution curves. Thus, even though we have not found any solutions and no graphs of solutions appear in the figure, we can nonetheless draw some qualitative conclusions about the behavior of solutions. For instance, if v is less than a certain critical value, then all the line segments have positive slopes, and the speed of the falling object increases as it falls. So maybe let's figure out what the v value should be here. We can see the line segments have positive slopes, so we go to find the segments with positive slopes. And in this figure, maybe these segments, they have the positive slopes. On the other hand, if v is greater than the critical value, then the line segments have negative slopes. And maybe these segments, they have negative slopes. And the falling object slows down as it falls. What is this critical value of v that separates objects whose speed is increasing from those whose speed is decreasing? Referring again to equation 5. Let's see. This is equation 5. We ask what value of v will cause dv over dt to be 0. The answer is v equal to 5 times 9.8. So how does it come from? Let's figure out it. We let dv over dt be equal to 0. So we let this dv over dt equal to 0, then we can get V is equal to, let's 5 times 9.8, because we can put this term on the right, and then we multiply 5 on both sides, so we can get V is equal to 5 times 9.8, and this is 49. Yeah. In fact, the constant function v of t equal to 49 is a solution of equation 5. To verify this statement, substitute v of t equal to 49 into equation 5 and observe that each side of the equation is 0. So let's do this. Now let's consider V is equal to 49 constantly. So now dV over dt is equal to 0 because it's a constant function, constant value function. This is on the left side of this equation 5, and then on the other hand we calculate the right side of equation 5. It's 9.8 minus 1 over 5 times V. Now V is constantly equal to 49. So this is 9.8 minus, this is I think this is 9.8 because 5 times 9.8 is equal to 49. So 49, we divide 49 by 5 is equal to 9.8. And then this is equal to 0. So for the equation 5 at this moment, the left hand side is equal to 0 and the right hand side is also equal to 0. So the V is equal to 49. This situation or condition is satisfying this original equation. Because it does not change with time, the solution V of t equal to 49 is called an equilibrium solution. Basically, it is a constant value. It is the solution that corresponds to a perfect balance between gravity and drag. In figure 1.1.3, we show the equilibrium solution V of t equal to 49, here 49, superimposed on the direction field. I mean here is 49, this position. From this figure, we can draw another conclusion, namely that all other solutions seem to be converging to this equilibrium solution as t increases. This means that on the above seems converge to this line, and in the below this seems to converge to this line. Thus, in this context, the equilibrium solution is often called the terminal velocity. The approach illustrated in example 2 can be applied equally well to the more general differential equation 4. So here this equation is equation 4, where the parameters m and gamma are unspecified positive numbers. The results are essentially identical to those of example 2. The equilibrium solution of equation 4 is the constant solution v of t equal to n times g over gamma. So how does it come from? Just if let's assume for this unspecified positive numbers m and gamma. So for m positive numbers, it is greater than 0. We can divide this equation, the left side and the right side, by m. Then we get dv over dt is equal to g minus this gamma and v and this m. And then at this moment, we let this dv over dt is equal to 0. So we can let it be equal to 0, and then we can get this v. The solution of v should be mg m times g n over gamma. This is for gamma greater than 0. So this is how this term come. Solutions below the equilibrium solution increase with time. It is like this. Below the equilibrium solution, below is increased with time, and those above it decrease with time. This sentence means that if we look at the segments below this equilibrium solution, the slope is positive. So the segment is, we can see it is a tiny part of the real specific concrete curve, and it is going increase. So the value, this is V, is going to bigger, namely the value of V is increasing, and above this line the value of V is decreasing. As a result, we conclude that all solutions approach the equilibrium solution as t becomes large. All solutions approach the equilibrium solution as t becomes large. So we look at this t-axis, and maybe we can Now we look at this trend or direction. You can see that as T becomes large, all segments they look like to be converging to this equilibrium solution line. Direction fields. Direction fields are valuable tools in studying the solutions of differential equations of the form. Let's write this equation here, maybe here. This is the dy over dt is equal to f of t and y. This is the sixth equation, where f is a given function of the two variables t and y, sometimes referred to as the weight function. A direction field for equations of the form 6 can be constructed by evaluating f at each point of a rectangular grid. At each point of the grid, a short line segment is drawn. Just look at this figure. A short line segment is drawn whose slope is the value of f at that point. Thus, each line segment is tangent to the graph of the solution passing through that point. A direction field drawn on a fairly fine grid gives a good picture of the overall behavior of solutions of a differential equation. Usually, a grid consisting of a few hundred points is sufficient. The construction of a direction field is often a useful first step in the investigation of a differential equation. Two observations are worth particular mention. First, in constructing a direction field, we do not have to solve equation 6. This means we do not have to get the real y. What is the y of t? We do not have to calculate or get that solution. We just have to evaluate the given function f of t and y many times. Thus, direction fields can be readily constructed even for equations that may be quite difficult to solve. Second, repeated evaluation of a given function and drawing a direction field are tasks for which a computer or other computational or graphical aid are well suited. So this figure is drawn by a computer. All the direction fields shown in this book, such as the one in figure 1.1.2 and 1.1.3, were computer generated.